Hello.
Hi.
So, is there anybody who does not have a TA evaluation form? Okay. Does everyone have a TA evaluation form? So, you have TA evaluation forms. We have 10 minutes for you to fill them out, so please fill them out. Also, if you haven't done the online instructor evaluation, that would be helpful because I always want to learn what to do different and what to do better. So please fill out the online instructor evaluation if you haven't done so already. So if you don't know your TA's name, just put your tutorial number and they can figure it out that way. This is the last lecture of the course. So we wanted to finish up with orthogonal diagonalization. And let me remind you of the difference between regular diagonalization and orthogonal diagonalization. So if A is a square matrix, then the first step is find all eigenvalues. So lambda 1, lambda 2, up to lambda k. So there might be n distinct eigenvalues, or find all eigenvalues. So that's a distinct list. Step 2 is for each eigenvalue, find the corresponding eigenspace. So E lambda I is the zero vector, and all eigenvectors with eigenvalue lambda I. Find a basis. Find a basis for each of these eigenspaces. Step 3 is construct a matrix P whose columns are the basis vectors. And if P is a square matrix, then A is diagonalizable. If P is a square matrix, then A is diagonalizable. And you would then construct a diagonal matrix D so that A times P equals P times D, which tells you that A is equal to P, D, P inverse. So this is the method that you apply for any square matrix. Someone gives you a square matrix, you can certainly find its eigenvalues. You can certainly find the eigenspaces. And in the process of finding the eigenspaces, you'll find a basis for each eigenspace. You can certainly construct the matrix P out of the basis vectors. The risk is that P will not be a square matrix, that you might not have enough basis vectors. So it's at this step right here that you decide whether or not a matrix is a diagonalizable matrix. So if P turns out to be a square matrix, then A is diagonalizable, and you can construct a diagonal matrix D so that A times P equals P times D, and you're done. And this is the process of diagonalizing a matrix A, if it can be. if A is a symmetric matrix, so that means that A transpose equals A. The first step is the same. The second step is the same. But now there's a step 2.5. If the dimension of one of the eigenspaces is greater than 1, apply Gram-Schmidt to the basis to create an orthogonal basis for that eigenspace. And now there's a step 2.75, which is normalize each basis vector to have length 1. And this will force, okay, sorry. Then step 3 is the same. Step 4, there P will always be a square matrix. So for a symmetric matrix, you will always have enough eigenvectors. I won't prove that. It's in the book. I don't recommend studying the proof unless you've mastered everything else. And P transpose will equal P inverse. That's because of something we're going to prove today. And then you construct D so that A times P equals P times D, and that implies that A is equal to P D P transpose. So this is, the right-hand side is orthogonal diagonalization, and it's something that you do for symmetric matrices, and it's called orthogonal diagonalization because P is an orthogonal matrix. Yes.
Isn't it P transpose, not P?
Oh, sorry, thank you. That is P transpose. Thank you. PDP transpose. Yes.
Do you get like the eigenvectors for a square matrix? If we Gram-Schmidt them and try that, will it work?
You can certainly, okay, so the question is, so let's imagine that we have, so A is 3 by 3, and it has eigenvalues 1 and 2 and 2. Then the dimension of the eigenspace, if you look at all of the eigenvectors with eigenvalue 1, what is the dimension of that eigenspace going to be? 1. And so its basis is going to be the vector v1. The dimension of the eigenspace for eigenvalue 2 will be 1 or 2. Okay, so 1 or 2. So if we had the matrix 1, 0, 0, 0, 2, 1, 0, 0, 2, then the dimension of the eigenspace would be 1. But it's going to be 1 or 2. If it's 2, so if the dimension of the eigenspace is 2, then it has a basis which is V1, V2. If we do Gram-Schmidt, that's going to give us a new basis, which is W1, W2. And that's a new basis for the subspace E2. So any linear combination of eigenvectors will still be, if you have eigenvectors that are eigenvectors for the same eigenvalue, any linear combination of them will still be an eigenvector for the that eigenvalue. So this will be a new basis, and it'll be mutually orthogonal. I should say V2 and V3, because I've got a V1 up there. So you've done Gram-Schmidt. These are mutually orthogonal. The big question is, are they orthogonal to this one? That's the big question. So you can certainly do Gram-Schmidt on any of the eigenspaces, but the fact that E2 is orthogonal to E1, that these two eigenspaces are orthogonal to each other, that's if and only if A is symmetric. So you can certainly get a nice orthogonal basis for an eigenspace, but it's not going to help you create an orthogonal matrix unless you have that the separate eigenspaces are also mutually orthogonal. Yes?
Basically, you might need to ask again about why you can't Gram-Schmidt across eigenspaces.
Okay, so this is, okay, so this is thank you for reminding me. So, question. Is a linear combination of eigenvectors still an eigenvector? So let's stick with our example. We have V1, which has eigenvalue lambda equals 1. And we have V2 and V3, which have eigenvalue lambda equals 2. All right? So I'm going to first try a linear combination of these two. So let's look at C2 V2 plus C3 V3. It's a linear combination of these two. Is this an eigenvector of A? So if anyone ever gives you a vector and says, is this an eigenvector of A, you have to test it. So what you do is you multiply it with A, and you see what happens. So A times C2 V2 plus C3 V3 by the properties of matrix multiplication, which plays nice with scalar multiplication and addition, is C2A times V2 plus C3 times A V3. So what is A times V2? And what is lambda for V2? 2. And what is A times V3? And lambda for V3 is 2. So this is equal to 2 times C2 V2 plus C3 times V3. So is C2 V2 plus C3 V3 an eigenvector of A? Yes. This tells you that E2 really is a subspace as long as you include the zero vector. E2 is the zero vector and all eigenvectors with eigenvalue 2. And so if we do Gram-Schmidt to a set within E2, it'll stay within E2, and any linear combination, because Gram-Schmidt is just a bunch of linear combinations, so Gram-Schmidt is not going to break E2. And Gram-Schmidt's not going to break any eigenspace. But let's try a different question, which was, can I do would it be a good idea to do Gram-Schmidt on this? So what Gram-Schmidt would do is it would give me W1, which I would probably take to be V1, and the second vector, W2, would be a linear combo of what two vectors? V1 and V2. Now, certainly, W1 and W2 will be mutually orthogonal. W1 is an eigenvector, so it's just a question of if W2 is an eigenvector. Or did Gram-Schmidt screw up the entire eigenvector concept? So W2 is C1 V1 plus C2 V2. I want to know whether this thing that Gram-Schmidt gave me is actually an eigenvector. So I hit W2 with the matrix A, and I get C1A V1 plus C2A V2, which is C1. What is A times V1? What's lambda for V1? 1. And what is A times V2? 2V2. And the question is this some number times C1 V1 plus C2 V2? Because if it were, that would be the eigenvalue. So yes, you can do Gram-Schmidt across eigenspaces, but the result will screw up the eigenspaces. Does that make sense? Okay. Are there, yes?
Not related to this. In step 2.5, like, why is there that modification? Like, why do we do that?
Because we're trying to get orthogonal we're trying to get an orthogonal set of basis vectors. So there are two things going on. So let's stick with this 3x3 example. So imagine A is 3x3 with eigenvalues 1, 2, and 2. Now, if A transpose equals A, so if A is symmetric, then E1 is going to be automatically orthogonal to E2. This I need to prove. So this means that if I have a basis for E1, and if I have a basis for E2, so that's an E1 basis, that's an E2 basis, I will get that V1 is orthogonal to V2, and V1 is orthogonal to V3. That's what I get for free if the matrix is symmetric. But now my question is V2 orthogonal to V3? Is there any, there's no, when we actually do calculations, we find that they don't come out automatically orthogonal, but it's not guaranteed. So what I do is I do Gram-Schmidt, which transforms V1, V2, which is a basis for E2, into V2, V3, into W2, W3, which is a different basis for E2. And so now I can ask, is W2 orthogonal to W3? Yes, because Gram-Schmidt. is W2 orthogonal to V1, and is W3 orthogonal to V1? So are they orthogonal? Yes. Because this is an eigenvector for eigenvalue 2, and this is an eigenvector for eigenvalue 1, and I still need to prove that eigenspaces are mutually orthogonal when I have symmetric matrices. But these are going to be yes by the same theorem that I still need to prove. But now at this point in the game, I have W1, W2, W3. These are mutually orthogonal. I can now make them unit length. I can construct the matrix P, and I'm off to the races. Yes?
So when you apply the Gram-Schmidt here,
Yep,
you're only doing it within eigenspace.
exactly. If I go without the eigenspace, I will break everything.
Right. Okay.
Yes? Where? Here I'm talking about the Gram-Schmidt vectors, and I'm comparing them to the eigenvector for this eigenspace. So you're asking about... Oh, thank you. Thank you. V1, thank you. Yes?
If A were
4 by 4?
yeah, 4 by 4 matrix, then we wouldn't have set that, or would we have?
Well, if it were a 4 by 4 matrix, then maybe I would have thrown in a fourth eigenvalue, and I would have had 4 eigenspaces, E1, E2, and E pi. These two are mutually orthogonal by the theorem I haven't proven to you yet. These two are mutually orthogonal by the theorem I haven't proven to you yet. These two are mutually orthogonal by the theorem I haven't proven for you yet. So here I would have V1. Here I would have V2, V3. Here I would have V4. Mutually orthogonal, mutually orthogonal, mutually orthogonal, orthogonal, orthogonal. I would still need to do Gram-Schmidt on these two. So basically, whatever the size of the matrix, whenever you have an eigenspace with more than one eigenvector, you need Gram-Schmidt. Yes?
Since V1 is orthogonal to V2 and V3, it's orthogonal to all linear combinations.
Exactly.
Which is why if we transform to W1 and W2, it's still orthogonal.
Exactly right. Exactly right. So let's just, what Jean just said was if V1 is orthogonal to V2 and V1 is orthogonal to V3, then V1 is orthogonal to any linear combination of V2 and V3. And that's just because you would compute the dot product C2 V2 plus C3 V3. And that's going to be C2 V1 dot V2 plus C3 V1 dot V3. This equals what? 0. And this equals what? 0. So this equals C2 times 0. C2 times 0 plus C3 times 0, which is 0. So this is why when you do Gram-Schmidt, you don't actually have to go back and check the orthogonality with the earlier ones. Yes?
Behind you, you said E1 is perpendicular to E2, and then you said the basis for it is V2 and then V2.
Oh, God. I'm sorry. I'm so sorry. I think it's free of mistakes now. Yes?
For the V1 and V2 on the right, are they already orthogonal?
No. So when I go through the process of finding the eigenspace, it's not guaranteed that they'll be automatically orthogonal. So I did an example like this in class on yesterday, where I started with so I had A is 0, minus 1, 1, minus 1, 0, minus 1, 1, minus 1, 0. The eigenvalues were 2, minus 1, minus 1. I had that the eigenspace for the eigenvalue 2 was the span of the vector 1, minus 1, 1. So that was V1. The eigenspace for minus 1 was the span of the vectors 1, 1, 0, minus 1, 0, 1. These are the vectors V2 and V3. So you can check that these two vectors are orthogonal. These two vectors are orthogonal. But these two vectors are not orthogonal. I then do Gram-Schmidt, and I get that E minus 1 is the span of the vectors 1, 1, 0, and minus 1, 1, 2. This is W1, W2, W3. W2 and W3 inherit being orthogonal to V1, and they are mutually orthogonal by Gram-Schmidt. And I know that Gram-Schmidt doesn't mess up subspaces. So when I go from this basis to this set of vectors, I know that the span of these two vectors is the same as the span of those two vectors. So that's Gram-Schmidt. Sorry, what? So V1 is orthogonal to V2 because A is orthogonal, is symmetric. V1 is orthogonal to V3 because A is symmetric. So A is symmetric guarantees that any vector here is orthogonal to any vector here.
But the thing that you just erased, it says W2 is a linear combination of V1 and V2, right?
I must have, W2 was a linear combination of these two vectors. So W2, I should have written W3 is some linear combination. Really, W3 is V2, V3 goes to W2, W3. This, I usually just take that to be V2. And W3 is V3 minus some linear multiple of W2. So it's a linear combination of this, which is an eigenvector, and this, which is an eigenvector, so it's an eigenvector. I feel like I've made things worse. Okay, yes?
On the right side of the blackboard, which you erased, you used the grand but it failed. But why on the left you used it again and used that?
So Gram-Schmidt, okay, so the question was, so here I'm doing Gram-Schmidt to two vectors that have the same eigenvalue. And because a linear combination of eigenvectors with eigenvalue minus 1 is still an eigenvector with eigenvalue minus 1, Gram-Schmidt ensures that this will still be an eigenvector with eigenvalue minus 1. If I do a linear combination of these two eigenvectors, this has eigenvector 2, this has eigenvector, this has eigenvalue 2, this has eigenvalue minus 1. A linear combination of these two will not be an eigenvector. So I don't know if it helps if you think of two subspaces. So here's E2, And here's an orthogonal plane, which is E minus 1. Any linear combination of vectors in the plane, it stays in the plane. Any linear combination of vectors in E1 stays in E1. But if I take a vector in E minus 1 and E2, is it still in either the plane or in the... No. So Gram-Schmidt just creates linear combinations. If you do Gram-Schmidt on vectors that don't live in the same eigenspace, you're going to screw everything up. So that's what I was trying to say on the part that I erased when he asked, was Gram-Schmidt can only be done within an eigenspace. If you go between eigenspaces, you break everything. Are there other questions? Yes.
Could you just prove what it is that you've been trying to do for the longest time?
Okay, so at this point, I think you would like me to prove that if you have a symmetric matrix and two eigenvectors with different eigenvalues, then they are different. So let's... So let me just be specific. So A is 3 by 3. A transpose equals A. And the eigenvalues are 7, 9, and pi. The eigenvectors are V1. Here are eigenvectors V1, V2, and V3. And I want to show that V1 is orthogonal to V2. If I figure out how to show that, then I'll probably be able to show that V1 is orthogonal to V3 and V2 is orthogonal to V3. Let's just see if I can show that. So my tools. So the first tool is that A times V1 equals what? 7 V1. My second tool is that A times V2 is equal to what? 9 V2. I want to show that the dot product of V1 and V2 is equal to what? 0. I also know that A transpose equals A. There are two things that I need in order to get anywhere. First is I need some way of relating dot products to transposes. And so that we already know. We know that U dot W is equal to U transpose times W. That we know. And what's confusing us is we would like to know something about the dot product of V1 and V2, but we would like to somehow involve the matrix A. And so that's where we can get someplace with the fact that they're eigenvectors. So here we go. So let's say A times V1, if I dot product that with V2. This looks like a weird thing to do, except that I know that A times V1 is basically the same thing as V1, right? So this is equal to 7 times V1 dot producted with V2. And similarly, I know that V1 dot producted with AV2 is going to equal V1 dot product 9V2. So that's 9 V1 dot product V2. So I'm doing all of this because I'm somehow trying to understand the dot product of V1 and V2. Have I used everything in my toolbox? Have I used that it's a symmetric matrix? No. So I need to use, yes?
Sir, why did you change from
because A is multiplying the vector v2. And v2 is an eigenvector with eigenvalue 9. And this is going to be the big thing. So I've used that v1 and v2 are eigenvectors. I have not used that A is symmetric. And so I'm going to somehow bring transposes to the party, which I'm going to do through the dot product. So A times v1 dot product v2 is the same thing as what times v2? A v1 transpose. So this is the product of an n by n matrix with a n by 1 matrix. So how does products play with transposes? They reverse. So that's v1 transpose A transpose v2 because of how transposes work. This is equal to v1 transpose times what? AV2. And this I used that A is symmetric. And this I can translate back to dot products. What is that? V1 dot product AV2. Okay? So now I'm ready to go. V1 dot product AV2 is equal to 9 times V1 dot product V2. AV1 dot V2 is equal to what? 7. V1 dot product V2. So what I have is, because A transpose equals A, 7 times V1 dot V2 equals 9 times V1 dot V2. That's the same thing as 0 equals 9 minus 7 times V1 dot V2. And that tells me that V1 dot V2 equals 0. So this is why if you have distinct eigenvalues and the matrix is symmetric, the eigenvectors are mutually orthogonal. So now let's see what would have happened if I had V2, which has eigenvalue pi, and V3, which had eigenvalue pi, and I had A transpose equals A, would there have been anything wrong with this part of the argument? No. This would have changed, and that would have changed. This would have led to 0 is equal to pi minus pi times V2 dot V3. So can I conclude that these vectors are orthogonal? No. Okay, so did this argument have to do with A being a 3 by 3 matrix? No. Did it have to do with the values 7 and 9? No. So let's just do the proof properly then, instead of by examples. So, theorem, if A is symmetric and V1 and V2 are eigenvectors with different eigenvalues then V1 is orthogonal to V2. So proof. We know A times V1 equals lambda V1, and A times V2 equals mu V2, where lambda does not equal mu. Then lambda V1 dot V2 is equal to A times V1 dot V2 is equal to AV1 transpose times V2 is equal to V1 transpose A transpose times V2 is equal to V1 transpose A times V2 is equal to V1 dot A V2 equals mu times V1 dot V2. Therefore, 0 equals lambda minus mu times V1 dot V2, which implies V1 is orthogonal to V2. Okay, where did I use that the matrix was symmetric? So here I used that I had an eigenvector. Here I used the definition of dot product. Here I used how transpose plays with matrix multiplication. Here I used that A transpose equals A. And here I used how the dot product is defined. And here I used that V2 is an eigenvector. Left-hand side equals right-hand side gives me this. And then I use that lambda does not equal mu. So the one thing I have not proved to you is that if you have a symmetric matrix, that you will actually get n eigenvectors, n linearly independent eigenvectors. I've proved to you that you can construct orthogonal eigenspaces. I haven't actually proven that when you build your matrix P, you'll get a square matrix. But that's not anything we can do quickly. So to finish up, true, false. If A is invertible, then it's diagonalizable. False. Counterexample. If A is invertible, then A is diagonalizable.
Shear matrix.
Beautiful. 1, 2, 0, 1. It's a shear matrix. If A is diagonalizable, then A is invertible.
False.
False. Give me a diagonalizable matrix which is not invertible.
0.
0, 0. Okay, there's the mathematician in the audience. Here's the engineer. True, false. If 3 is an eigenvalue of A, then 15 is an eigenvalue of 5A. True. Lambda eigenvalue of A implies C lambda is an eigenvalue of CA. True, false. If R is the reduced row echelon form of A, then the eigenvalues of R equal the eigenvalues of A. So A is row equivalent to R. This is in reduced row echelon form. Then the eigenvalues of A equal the eigenvalues of R. Okay, good. What's your counterexample? Well, you have to be specific.
1, 2, 3.
Anything in order.
Okay, what's the easiest matrix to write down the eigenvalues? Well, the problem with 1, 0, 0, 1 is that it's in reduced to echelon form. So you're being too much of a mathematician. So this is row equivalent to, what's the reduced to echelon form of that? 1, 0, 0, 1. Eigenvalues of this? Eigenvalues of that? Okay. So good luck studying.